Okay, so let's do an example of volume by slicing. Let's find the volume of a cone of radius 2 centimeters. I'm just going to use some units. Let's choose centimeters and height 5 centimeters. So if I draw the cone the same way I did on the previous video, it would look something like this, right? And we want it to be height 5 and radius, I guess that's the radius right there, radius 2. And we want to think about a slice, and that's a circle, right? And we think, okay, so we want to actually take that slice at height y. So again, we need a coordinate system. This is actually one of the most important things that you're going to do in every kind of these application integration problems is set up coordinates. So if this is a y-axis, then you could say, well, this right here is y equals 0, the bottom, the top is y equals 5. And so I just want the slice at height y. And then what we said is, well, we have a circle, that slice is a circle. We'd like to know the area of the circle at height y. So here's if we pull the slice out, it looks like this. That's a circle kind of from the side. And so the area, we want the area A of y. And then what we think about is we think of thickening it up a little bit to make an actual like sliver of width dy. And then our integral to solve this will be the integral from 0 to 5 a of y dy. So that's the setup. That's the setup for the volume by slicing. And make that look a little more like a 5. It's about the same. So anyways, the whole point is that's the setup, and then the whole question is to find the area of a slice at height y, right? Like, for example, we can even sort of see, like, think about what a of 0 is, the area at height 0. Well, that's just a circle of radius 2. So that's pi times the radius squared. So that's 4 pi. And if we did the area at height 5, well, the slices get smaller and smaller, and in fact, it kind of goes away. So the area there is just 0. So you want something like that, right? That's going to be 0 when it's going to be 4 pi when y is 0. It's going to be 0 when y is 5. And then the real question is, well, what is it in general? And so let me draw this. I'm going to call this like the side view of the. Move this a little bit, actually, just to get it out of the way. So I want to draw the side view. I'm going to call this the side view of the cone. So it's kind of like a cross section, like this side cross section, right? If we actually draw this, that's kind of like if you just slice the cone vertically, what you would get, you get this triangle. And so that's kind of, it's almost like we flattened it from the side onto like a 2D, or you think like the shadow of the cone or something if you shine a light from the side. So let me put the axes here again. Y equals 0, y equals 5 at the top. It's a y-axis. And then what we really want is we want to know the radius, right? So the radius, because that's if you go back over to the picture on the left here, that's kind of like that radius. That's the radius right there. It's kind of half the distance. So that's the radius. So let's call that r. But it's at height y. And we would like to know that radius. Again, at the bottom, the radius is 2. At the top, the radius is 0. But what is it at like height 1 or height 2 and so on, right? So this is how we have to think about this. I think that there's the big trick here is to use similar triangles. So actually, I'm going to draw the vertical here just because that's sort of nice. So let me think about this big triangle. We've got the big triangle here, the green. I'm drawing this green triangle. And then we have this smaller triangle, which is this red triangle. That's also a right angle right there. And I can draw these triangles sort of separately. Move this down a little bit. If I just draw the small triangle, let me draw the big triangle, the green one, right? If I draw this over here, okay, so that's the one triangle. And we know this is 2 and this is 5. My God, I cannot draw a 5. Okay, so that's 2 and that's 5. Now, if I draw the red triangle next to it, smaller. Oh no, okay. And the radius is r, or at the bottom of that triangle is r. How tall is this triangle? Well, if you think about it, this up here was at height 5, this is at height y. So the difference is 5 minus y. So that's actually 5 minus y. Okay. And we want r as a function of y, right? Because then the area is going to be pi r squared. But we can use some similar triangle ideas. If we want to think about similar triangles, you can remember the ideas that the ratios of the sides are the same. So for example, 2 is to 5 as r is to 5 minus y. So we can write 2 is to 5, 2/5 is r over 5 minus y, since those are similar triangles. And that actually means we can get a formula for r if we multiply both sides by 5 minus y. We sort of bring this up here. Then we get r is 2/5 times 5 minus y. Great. And then a of y, the area of at height y, is pi r squared. So that's pi times 2/5 times 5 minus y, all squared. And you can be a little bit, you can sort of, you're going to square the 2/5, so you're going to get a pi times a 4 over 25 times a 5 minus y squared. And you can check, actually, you can check that, like, for example, you know, a of 0, which we set up here was 4 pi. A of 0 is pi times 4 over 25 times 5 squared. And those cancel. And it actually is 4 pi, which we said it was. So that works. And also, if you plug in, you can sort of see almost instantly that when you plug in 5 for y, you get 5 minus 5. So that's just going to be a 0. Okay, so that does seem to work at the extremes. And then that's the function we want to integrate. This function right here is the function we want to integrate. And it looks a little bad, but so the volume, come back to it if we can actually compute the volume now. It's the integral of 0 to 5 pi times 4 over 25 times 5 minus y quantity squared dy. You could pull out the 4 pi over 25, right? That's, we just want to compute this real fast. This isn't too bad. And then I'm actually going to FOIL out the 5 minus y quantity squared. And if you do that, you can check this. If you FOIL out 5 minus y quantity squared, you get 25 minus 10y plus y squared dy. Right, that's just from foiling. Just multiply it out. 5 minus y times 5 minus y. And so now we can integrate. This isn't too bad. So we get 25y, 25 becomes 25y, minus 10y becomes minus 5y squared, plus 1/3 y cubed from 0 to 5. And again, that's not too bad. You plug in the 5s. Plugging in 0 actually gives you nothing. So it's 4 pi over 25. So we get 25 times 5 minus 5 times 25, 5 squared, plus 1/3 times 5 cubed. So we get that minus 0, really. When we plug y equals 0 into all those terms are going to go away. And there's some interesting stuff that goes on here. I mean, it actually simplifies quite drastically. 25 times 5 and 25 times 5 go away. This is 5 cubed. We've got a 5 cubed here. We actually have a 5 squared here. And so we get 4 pi over 5 squared times 1/3 times 5 cubed. So we get cancellation. And there's a 5 there. So I think we get a final answer of 20 pi over 3. And since the links were in centimeters, this is actually in cubic centimeters. And there's your answer. So that's kind of a volume by slicing problem. Just remember, the big idea was to use similar triangles up here. Okay. So I'll probably also show you a slightly slicker way to do it. It turns out you could, I'll just say this now, you could actually flip the cone upside down and put the point at y equals 0. And it's a little bit nicer. The algebra and everything's a little bit nice. You get the same answer, but you can do that. Okay, so there's an example. All right.